Yes, to Zebida. You can just unmute. To Zebida, you can just unmute. Just unmute and tell us.
So for me, what I think it's an algorithm in a data set which shows the frequently appearing items.
Sorry, can you repeat that if you don't mind? It's us?
So in my opinion,
Yeah.
it's a algorithm that identifies frequent appearing items in a data set and which creates a relationship in it.
Yeah, I think that is it with a priori. So let me just start with we start with some theory here so that we can understand at least terms used in a priori algorithm. Then we get into the implementation. In fact, just I have a theory part here that I would like us to go through. Because in this priori algorithm, we have terms that you must understand before even thinking of implementing it. So, and we start by defining what a priori algorithm is. And we are saying that a priori is a frequent item item set mining algorithm. So I think you should underline that a priori is a frequent item set mining algorithm, and basically it is used in association rule learning. So let's see, we are told that it helps uncover relationships that is between items in large data sets, typically used in market basket analysis. So, and we have an example like finding which product are frequently bought together. So it's kind of an algorithm. In fact, this one is it's a perfect example of the example that I gave yesterday. So basically, this one is used mostly to do the basket analysis. That is, I'm sure you guys you go to supermarket and do some shopping. So and I think you put all your items in those baskets, right? So now we have we, the, you can use this priori algorithm, or the owner of the supermarket can use they can hire a profession to analyze on what people buy together, or what is bought frequently together. So I think this was the example that I gave yesterday. It was supposed to be in the a priori algorithm, but also in k-means, though it isn't directly used. Um, but for a priori algorithm, I think the perfect example is the basket analysis, and this normally happens in the supermarket. So basically, that is a priori algorithm. And I feel that we should understand some of the terms that are used in the a priori algorithm implementation. And one of the terms that is used in a priori algorithm is the antecedent consequence. So in a priori algorithm, we check the relationships using the if and then. So if this is bought, uh, then what? So we have the antecedent on the left side, and we say that antecedents, that is the items on the left side of the rule, that is the if part, and then we have the consequence. That is the items now on the right side of the rule, and which is the then part. So let's see an example here. I think with an example you're going to understand the if then relationship. So I have an example here where we have a rule. We're just assuming that in the supermarket, maybe you want to buy a bread. So that one in this rule, the bread will be the main item that you want to buy, and the butter will be the consequent. That is on the right. So meaning that if a customer maybe buys a bread, so this is now the if part of this the if then relationship. If the customer buys a bread, then what else does he or she buy? So now the then part, or what we are calling the consequent, we have the butter, right? So we have antecedent as the bread, and the consequent as the butter. So maybe we are assuming that any person who buys, or maybe any person who buys a bread, the likelihood of buying butter, maybe it can be high or low. We don't know because we are yet to check this. But basically, that is how the antecedent and consequence mean in the what in this basket analysis in a priori algorithm. I don't know if there is a question so far before even we get to other terms, but basically that is the meaning of antecedent and consequence. Um, if no question, let's proceed to the next term that you should understand is the something we call the support. And support measures how frequent an item set appears in a data set. So assuming you have a data set of 1 million items, let's not use a million. Maybe let's say maybe you have 200 items. So the support will measure how frequent an item out of the 200 items appears in that data set. Let's say maybe bread, because we understand that an item set is whatever now. Okay, all the items that you put in that basket, right? So that is what you are calling item set. So the number of times that bread will appear in all the maybe the item sets uh, or maybe baskets in the people who are doing the shopping in that whatever in that supermarket. And there is a formula to calculate the support. We talk of the number of transactions containing the item set, and divide the total number of transaction. Let's have an example here. Suppose we have this item set of bread butter appears in 15 out of the 100 transactions made in that day. So to calculate the support, it will be now 15 divided by 100, which is approximately 15%. That is now the support. So something that you should understand here is the number of transactions containing the item set. So this is just one item set. In the supermarket, you have many items, but in this example, we are just checking the bread butter item set. There might be another person who is maybe who is buying bread butter, then Colgate, I mean toothpaste, and maybe uh, some soap, detergents. But in that item set, it still has butter, breaded butter. So meaning that we are checking the item sets that contains the bread and butter. So that is what we are counting. Out of 100 transactions made in that day, we have at least 15 of those transactions or of those item sets containing breaded butter. And now to measure the support, it is now 15 divided by the total transaction. That is the formula that is used to calculate the support. The other term that I want us to check is what we call the confidence. And the confidence will tell us how often the rule is the rule is correct. So you notice in the definition that we were talking of, we were talking the association rule learning. So that is the association between maybe two items. It can be 3 items or maybe 4 items. So to measure the confidence here, we have a formula that is used, and we use that is the number of the transactions. In fact, we can talk about the number of transactions. I think I didn't put that icon here, that screenshot, but it should be the number of. We have it here. You can talk of bread butter appears, let's say, in 15 transaction. But how many times does that bread how many times does bread appear alone in any shopping done in that supermarket? So now we are going to take the number of transaction that bread butter appears divided by the number of times bread maybe the shopping done in the supermarket. That is bread appearing alone in an item set of any shopping done in that supermarket. And that is why now we are taking 50, we divide by now 20, and we are getting a value of 0.75, which is equivalent to 75%. So meaning that that confidence is quite okay in this case. And we are saying that the higher the percentage of confidence means that the rule is more reliable. Sawa. Um, let's get to the fourth one. That is the fourth term that I want us to check. And it's a term that is called the lift. The lift will measure how much more likely the consequent is given the antecedent compared to the random chance. I don't know if you guys will understand that. It's just measuring how much more likely the consequent given the antecedent. I think by now you should understand what I mean by consequent and antecedent compared to the random chance. So let's have an example here. We are talking of an example of a bread butter again rule. So where we have now our confidence here is the confidence is 0.75, and we have seen that the butter appears in we are saying that the butter appears in 30% of the transaction, which is now the support, that is 0.3 or 30%. So the lift now here is 0.75. We divide by 0.3, which is 2.5. So let's see how we interpret these values. When the lift is equal to 1, we say that there is no association. That means, to say that there is no association, that means that buying a bread does not affect the buying of the butter. But if the lift is greater than 1, that is a positive association. And we are saying that buying bread makes buying butter more likely. So this is why I was saying yesterday that should there be a positive association uh, when you implement your a priori algorithm, that means this one can influence, just having a positive association. This one can influence the owner of the supermarket to authorize that um, where bread is kept in those shelves, the butter should also the butter should be somewhere close to. I mean, butter should be somewhere close uh, where bread is positioned or is put in the shelves in the supermarket. Simply because now we have a positive association to mean that buying a bread will make buying butter more likely. I don't know if you guys you are getting that. I don't know if you guys you are getting that. Thumbs up if you are understanding what I'm trying to talk about. Yeah, I can see Rodovan, they have Grace, David, Erickson. What about the rest now? Stella, are you getting it? Mombi, are you getting what you are talking about here? Yeah, I can see Mombi also is getting what you're talking about. So now when we have a lift of maybe less than 1, that one is a negative. That one is a negative association, and we are saying that buying bread reduces the chance of buying butter. So meaning that now using such kind of algorithms can influence how things are positioned in, or how they are put in shelves in a supermarket, or in any area that we do our shopping. So those are some of the these are some of the what these are some of the terms that uh, that are important to understand before even we get to the implementation of a priori algorithm. Just try to understand them. I think I should share this file with you. Yeah, I'll share this file with you. So let's get into the implementation of this. I shouldn't take much time because I've already done that. Just going through the code. Let me just try to reconnect these. Uh, you notice that today I have not sent any dataset simply because I'll randomly generate the dataset. I want to show you how you can do it. So I'll just I'll import random, and I'll also import the pandas SPD. So what I'm going to do is I'll have the products that I'm assuming they are in a certain shop, and those products I'll put them in a list. And some of the items that I'm putting in a list is milk, we have bread, we have We have butter, we have egg, we have cheese, we have juice, we have cereal, we have yogurt, we have apple, and banana. So I'm assuming that we have a shop or maybe a mini supermarket that sells all of these. Then I'll maybe try to generate 100 rows of transactions, or maybe I can try and generate maybe something to do with 500. I'm going to generate 500 rows of transactions. That is random transaction. I think I should indicate they should be random. Um, yeah, just copy this. Oops. I think I'm yet to fix my keyboard here. Yeah, generate random 500 rows of transactions. So, and those transactions again, I'll put them in a list. So you can see that I have an empty list here, and I'll have these for loop that will help me generate those 500 rows of transaction. Uh, I'm just saying that the number of items in each transaction should be two to five, and then I'm just taking now the random samples. That is, I'm just trying to generate the random samples. That is why I'm using random dot sample, and then I'll pass in this function. I'll in this method I'll just pass my product in the mini supermarket. Then I'll pass the number of items that I want in each transaction. It's just that easy. And then I'll append all the transaction in my transaction list here. So it's just that easy. With that for loop, I should be able to generate that. So let's see. Okay, let's see how this works. Uh, I think I should. Let me just separate these. Yeah, I think they should be in here. So after generating these, it will be a list of it will be a list of maybe a try. Let me just try to print these transactions. They should. Let me also separate these. So I don't know if you can see what I have. These are the item sets that I was talking about. You can see the first item set. I have banana and juice. I have the second one. I have an item set of yogurt, cheese, eggs, apple, and cereal. So if you were to go through all these, you notice that each and every item set it has how many items it has a length of not more than five. It's either four 2 or 3, simply because we said that we defined here that the transaction they should have 2 to 5 items. So these now with these, I can convert now this one to a data frame that we are going to work with. So, and that is the reason why I want to convert those transactions into a data frame by using the data frame, the pd.data frame function. I think you guys by now you know how we do it. So df is equals to pd dot data frame. Then we pass in the transaction. Then we can convert this one to a CSV file by saying df to CSV, and we don't have to have an index. And then we just maybe try to bring the first 30 items. So let's run that. And now simply you can see we have our CSV file already now created. So you can see at 0 index we have just 2 items. That is a banana and a juice. The rest are none, simply because now we define that the maximum number of items that should be in an item set is 5. That's why you can see none in the third item, in the fourth, in the fifth. That's why you can see none. But for the other one, we have at least now with this one we have what there. We have a basket with all these items. That is the yogurt, cheese, eggs, apple, and cereals. You can just go through them together. We see how these items are distributed in various item sets. Um, you can also see like in index 4. So we have 5 items in that. Um, yeah. Also, when we get to 29th row, we have just 2 items. That is milk and cheese. So these all what we have here, these are now our item set. We are just assuming that this one is a simple transaction. John came in that supermarket and bought banana and juice. We can have Irene came and bought uh, bread, milk, cheese, cereal, and she put that into a basket, right? So this is just a recording of the transactions. I am hoping that you guys are understanding that. You understanding that. So those are the transactions that we have. So for now, our algorithm now to under you notice that our algorithm cannot understand this. We said that the computers will always understand there is one and zeros, right? The binaries. And now we have to the third step, we should convert this transaction into something we call one hot encoded format, so that we can convert this one into ones and zeros. Where we have an item, we call it a one. We have none, we call it a zero. So that now our priori algorithm will understand that easily. So that is what I want us to do. Yeah, in fact, it's just right here that a priori requires data in a structured one hyphen hot encoded format. So you can convert this one into trues and false, or one and zeros. So that is what we are going to do next, and we do that by using the transition encoder. That is what we're going to use, and we're importing this one from the ML extent dot pre-processing. You notice that all these functions, or all these attributes are in the pre-processing part, in the processing repository. All these functions so they are in pre-processing repo for now from the ML extend. So we can just import that very fast. Then we're just going to create an instance. I think by now you know how to create an instance of a certain function. And to create an instance of that, we're just saying that we are equating this function to a variable so that it will be easier for us to use it. So that is what I'm calling the TE is equals to the transaction encoder. Then I'll just have there is this part now. We have the te.feed. We pass in the transaction, and we want to transform all those transactions. Then we have now a df encoded. We equating this one to now our encoded data. So you just pass in the t array and the columns with t columns. So if I try to maybe print the head of our data, the head of our data frame now, which is the df underscore encoded, if I just maybe try to run this, you notice that I'm getting values, these values of that is false. Let me just maybe try to pick the first 20. You notice that I'm getting values of now that is true and falses. But something interesting here, I've taken my all the items in the shop. That is apple, banana, bread, butter, cereal, cheese, eggs, juice, milk, and yogurt as my heading now. That is what I mean by when I talk of now columns is equals to te dot column underscore. Just that one just means that these are the names of the columns that I'm going to use. So now our transactions will, if let's say maybe James was going to a shopping, went to shopping and didn't buy apple, we are going to record that one as a false. You can see that James bought a banana. That one we are going to record that one as true, and even the other items. So in my basket here, uh, all the true means that I bought that item. That is now the transaction. Now with this one can a priori algorithm now will easily understand this, right? In fact, we can try to convert this one to one and zeros by just having this one dot as type int. We can convert this one to using this function. We call it as type. Then we pass in instead of getting the true and false, we can use the one and zero. So let's try to run this. And now you notice that I have one and zeros. I've just like converted the false and trues to one and zeros using this function. So any question up to that point? Okay, thumbs up if you are together up to that point. Yeah, I can see Tuze Bidari is okay. We have David, Mumbi, Aline. What about you, Sylvia? Good. So now with this now we can apply. We can now try to use the a priori algorithm. So we are just saying that we apply now the a priori algorithm, and we are talking of we can just maybe try to import these to import the a priori that is from the ML extent dot frequent patterns, and we import the a priori. So the a priori usually take a number of parameters, and even before we get to a priori just take a number of parameters here. And you can see that we are passing in the first parameter that we are passing in is our encoded data frame, that is df underscore encoded. Then we have the mean support, and we are saying that the mean support 0.1 means that the item set must appear in 10 or more transactions. So what did we say support is? If we were to get back here and try to check the support is the measure of how frequent an item set appears in a data set. And that is what we are saying, that it must, we are giving it a value of 0.1, meaning that an item set must appear in 10 or more transaction, so that now we can in fact this one we can just try, we can just change this one to 500, simply because we added that. So we are saying that we must use the mean support of 0.1, just to mean that in all the items that are going to be generated by these algorithm, or by what we are using, I mean by the algorithm, then those item set must appear in 10 or more transaction. So that is what we mean by the mean underscore support. We are giving it a 0.1, and in fact we are just passing that we must use the column names to, we are just setting that one to true. So let's try to print the frequent item sets that will be generated by this a priori algorithm. So we try to run that. You can see we have a number of item sets that are generated, and we always start with the individual item. You can see that we are starting with we have the item set that is apple, we have banana, bread, butter, cereal, cheese, eggs, juice, milk, and yogurt. Then from there, then we are going now to have at least now two items in a basket, and you can check the measure of the support here. All of these we have them as greater than what? Greater than 0.1. Maybe even you can try to change this one to something like maybe 0.3 to reduce the number of frequent items that you are going to generate. Let me just try to rerun this. And now you notice by just changing the mean underscore support value, we have reduced the number of items sets that we are going to generate. So the support 0.34, we have now apple. We have, I think we have just the individual items. So let me just return these so that at least we can accommodate multiple items in an item set. Let me just use 0.1. So that at least we can have a number of item sets. So these are now the items that we are going now to use to generate the association rules. Because we said here, let me just get back into what our definition of a priori algorithm is. We talked of a priori algorithm is a frequent item set mining algorithm. So meaning the algorithm here is just helping us to generate those item sets. Then those item sets are going to be used in the association rule learning. So, and basically that is what we are doing here. We have we have used the a priori algorithm to mine the item sets. Then now those item sets we are going to use them to generate the association rules. And we are saying that now we are talking of generating association rules now from the item sets, and we are talking of in fact when you're generating the association rule, we have a number again. We have a number of parameters that we are going to pass to our association rule function, and one of the parameters that we are going to pass here first is the frequent item sets. Now these item sets that we got or that we mined using the a priori algorithm. So those are or that is the first parameter that you are going to pass in the association underscore rules function. Then we are going now to have the metric. The metric in here, the metric can be a lift. You can use a metric as a confidence, and you can use a metric as support. Because I think by now you know what is support, what is the confidence, and what is the lift, so that now we can generate association rules based on based on the metric that you use. But in this case, I'm just using the lift, and we said that lift. Let me just get back here to the lift. We talked of the lift as the measure of how much more likely the consequent is given. We are talking of more likely the consequent is given the antecedent. So that is the metric that we are going to use. We want to see how we want to see how these how the antecedents affect the consequence. So that is basically the metric that we are using in our association in creation of these association rules. You must set a mean threshold, and we are setting that one to be is 1.1. And in fact, what we are saying that whenever we are talking of now comparing among all the rules that are going to be generated, we want the rules with a minimum threshold of 1.1 lift. So let's run these and see what will happen. And you notice that we just have an empty data frame. This to me, we did not manage to create. We don't have we don't have rules with the lift of 1.1. What if maybe we try with metrics where we have 1.0? Let's see what we have. Now you can see that we have a number of rules. We have a number of rules that have lift is that have lift is 1.0 and above. Maybe you can now check. In fact, I was just trying to print the rules. Let's analyze these. And we can see the where we have Apple as antecedent and having the consequences juice. We have these metrics here. The values of metrics are as follows. We have the support is 0.120, the confidence is 0.35, but our main focus is now the lift. I don't know if you guys are getting. Now, when you get 1.06 here, you get back to the interpretation here, whereby we say that a lift where we have value is equals to 1, we are talking of no association, right? But where we have a lift greater than 1, we have a positive association, right? So meaning that from this case here, because we have the lift as 1 is greater than 1, we have now the where apples are bought, the likelihood of buying juice, it's the likelihood of buying juice is more likely because we have the lift greater than greater than 1. What about now the areas where we have let's try maybe use um, let's have maybe let's check cases where we are using maybe a lift of 0.9. Let's run this because I'm supposed to get a large number of rules here. So in these cases where let's say let's try to analyze these baskets now, these transactions. Where we have banana and apple, we have the lift is the lift is 0.9. But now when we get back to our interpretation here, we are saying that where lift is equals to 1, no what? No association. Where lift is less than 1, there is negative association, meaning that buying of the antecedent reduces the chance of buying it reduces the chance of buying um, the consequent. I don't know if you guys you are getting it. This is how now. This is how you know you can use this a priori algorithm to determine which items you should put maybe close to each other during the arrangement in the supermarket or in a mini market. Basically that. So let's maybe try to use a different matrix here. You can maybe try to use confidence. I think I can just copy these. Oops. Let's give this one a threshold of maybe 60%. I think 60% will work for us. And also you can see it's kind of we have set the confidence uh, large value. So let's maybe try to use 0.5, which is translate to 50%. Still we can't get any rule. Let's maybe try and have 3%. I mean 30%. You know, here if you check keenly on our confidence column here, you notice that we have again we have our rules. I mean, we have confidence where we have greater than 30%. That is on the confidence column. So basically, now you can analyze again on you can analyze using the confidence. You can analyze using the confidence. Now, what uses metric is what you are going to use is what you are going to use to do the analysis. So I don't know if there is any question up to that point. Any question? Okay, thumbs up if you guys you are getting these. Does it mean it's just Tuesday Bidharu is getting it? Okay, I can see also the rest. So in fact, that is basically that is the implementation of a priori algorithm. That is that is the implementation of a priori algorithm. Um, just understand that a priori algorithm will just help us to mine the item sets in a large data set. I just used the random values. Just maybe try go to cargo and try and look for a data set. Just try to look for a data set and maybe try to follow these steps. I'll also share with this code with you so that you can try to implement it using a data set. Uh, yeah, I think that is it. Any question? I think I can just maybe pick two questions before we proceed to the next thing. Rodavan, any question?
I don't have necessarily a question, but yeah, today has been a bit, the a priori has kind of knocked me offside. Imeonyesha dust kidogo, but yeah, I'll try and catch up. Like on a deeper note, I'll go back to the video.
Okay, okay, okay. In fact, it's quite simple. It's only that I maybe I tried to generate data randomly, but always you have you can maybe you can maybe try and get a data set from cargo, and this is where you're going to this is where you're going to read your data set. In fact, the other steps are you're just going to use the steps that we have used here. That is using the one hot and encode format that is on the dataset. Then after that, you use the a priori algorithm to generate the item set, and then from there you try and generate strong rules. That is from the frequent item sets, and then now you can try to do the analysis of now what you can maybe now try to analyze the rules that you have got from the association underscore rules method. So basically that is it. Maybe when you guys you'll follow this video so that at least you can try and understand better. In fact, this one is uh, it's not that quite straight comparing it to other algorithm, and not everybody uses these. So yeah, I think I'll just go like to go through it at your own free time, so that you guys you can